Now for chapter 13, this chapter is dedicated for the non-structural component. However, according to ASCE, if the weight of the non-structural component is more than 25% then of the effective seismic weight, then the component shall be classified as a non-building structure. So if I have a building, okay, and I have a machine here, like maybe I have a horizontal vessel, okay, and maybe I have here two heat exchangers. This type of equipment, it is in oil and gas. Okay, may I have something called an air cooler. So if the weight of these vessels, so any weight of equipment is more than 25% of the W effective, which is may concentrated in the dead load of the body of the structure and the superimposed dead load. It is the case. If it is more than, then I can consider it as a non-structural building. In this case, of course, in the horizontal vessel and the heat exchanger and the air cooler, no, so it is non-structural building, not similar to building. So I will have to solve them with chapter 15. However, if their W equipment is less than 25%, then chapter 13 I will go to this chapter as we will see now. Another important thing you must notice that the importance factor IB is equal to 1.5 for essential buildings and IB is equal to 1 for the others, meaning that the importance factors for the equipment, they are 1.5 or 1, like the row 1 or 1.3. There is no 1.25 for the non-structural component. The most important part is that we will talk briefly about this chapter. The most important to calculate the horizontal force and to understand how to apply this equation, because as you can see that is an AB factor that is related to the equipment, the SDS which is the same that we already calculated in chapter 12. We will have to multiply the FA multiplied by the SS to get the SMS and then multiplied by 2/3. The WP, it is representing the machine or the equipment weight. The RB and IB, it is also related to the equipment, and you will have to multiply it by a factor which is the maximum value of this. It can be ranging from 1 or 3. So now if you have like a building here, it consists of 3 stories, and the first story it has like an equipment W1, and another one is W2, and the third one is W3. And in the exam he gave you like a relationship between each of them. So this W1 is equal to 2W2 is equal to 3W3. Okay, so I have a relation, and he gave me the height of each story that is located each equipment. So and he will tell you which one will have like a higher forces and so on. So to apply the equation, maybe they have the same type. So the AB and the RB and the IB, they will be the same. However, the location is different. So this factor of 1 plus 2 multiplied by z divided by h, the h, it is related to the total height of the building. Okay, so if I have like equipment at this location, so the z equal be 0. Okay, so and it will have no effect on the building. But let's talk about W3. So for the factor of W3, it will be 3, and this W, it will be corresponding from ranging from 3 to 1, and this one W1, it will be lesser than that. So the highest value, the Z, it is the location of the building. So this case, the Z, it will be H1, and the Z here for the equipment 2 will be H2, and the H3 it will be the same as H, so it will have a value of 3. So it is a good practice to understand this equation, because Also, it is important to consider it if he brought you something like an equipment. You have an equipment, and I want to calculate the seismic force. Then the first thing, the rule of thumb, if it is less than 25%, I will use this chapter. If it is more than 25%, then I will go to chapter 15. Okay, and we will talk about chapter 15. Of course, the other the risk category is whether the IP is 1.25. There is no 1.5. It is whether it is 1.5 or 1. As you can see here, the component importance factor shall be taken as 1.5 if any of the following conditions apply. So it is important to read these conditions, and all the other components shall be equal to 1. So there is nothing, there is no 1.25 as same as the structural building. Also, it is important to define the seismic force. It is the same as the one that we already calculated in chapter 12. It has the same value of 0.2 SDS multiplied by the weight of the equipment. That is the equation that I am focusing on. The AP factor, it is like the rho. It has two values, 1 2.5, the IB 1 to 1.5. There is no mid value. So if he tried to talk to you that the AB can be ranging from a value like 2 and so on, no, it is black or white. Also, this table, that is the one, that is a coefficient for architectural components. So if you want to design like an architectural components, that is the one. Okay, because it is components. As I told you, that is like chimneys. Then you will have to use this one. Laboratory equipments, other rigid components. So it is very important to consider that if the component is rigid, if its time period is lesser than 0.06 seconds, then it will be considered as rigid, and the AB it will be 1. For the flexible component, if the time period is more than 0.06 seconds, then the AB it will be 2.5. Wow, that is a very high value. So I will multiply this equation by a factor of 2.5. Okay, so it is important to consider the weight of the equipment and to consider the rigidity. The weight, it will lead me to chapter 13 or chapter 15. The rigidity or its stiffness, it will lead me to use an AB 2.5 or not. So it is so in here, if he tells me that this equipment is flexible, okay, say so I will have to multiply by a factor of 2.5. If it is rigid, then the AB is equal to 1. So in the exam, if he bring me a building with 3 different equipments having a relationship of each W and maybe a relationship with the H, and he tells you arrange them ascendingly or descendingly, so it is important to consider the rigid, meaning that the AB equal 1, flexible 2.5, and so on. The location is this one, due to its height, it will have a higher forces. So it is a good idea to understand the behavior of each one of them. Also, you mustn't forget that in this case, of course, they have the same SDS. Okay, so if you divided each one of them, you can get a relationship for the FB. Also, the FB is not required to be taken at greater than this value and less than this one. That is also the vertical force component. Now let's go and talk about chapter 15. As I told you, chapter 14 I will pass it because this one I think it's related to the material. You should have a light reading about it. It is a material specific seismic design criteria and so on. So it is important to have a light reading. I think it is like maybe 5. So 8 pages. Maybe if you have enough time, you can just read it. If you don't have enough time, then you can pass it. Okay, so we will talk about chapter 15. It is for the non-building structures. Non-building structures supported by the earth or supported by other structures shall be designed. It is very important to read the start of the general, because it will lead you or it explains the idea of this chapter. Yes, non-building structures supported by the earth or supported by other structures shall be designed and detailed to resist the minimum lateral forces applied. Okay. Also, structure analysis procedures. It is very interesting in this part. Because if I have a non-building structures that are similar to building, so I have like a structural building, a process structure, it carries equipment and used for operation and maintenance, so it will behave the same as a building. Okay, this one, it will behave the same as a building. Also, I have the same resisting systems. I am using like special moment frame, I'm using a concentric braced frame. Okay, so it will have a selection. This one can be designed according to the effective length method according to chapter 12. I will go past the other slides and talk to this one. The first thing, if you have the W of non-structural component is lesser than this one. So let me start and from this position. So I have the same building also, and I have equipment located here. Maybe I have an air cooler. So to consider the air cooler, don't forget about the from chapter 13. It tells you that the equipment here, okay, the W equipment must be less than 0.25 the W total. Okay, so in chapter 15 it is still tells you that for case A, that is the case A, the WB must be, if it is less than 0.25 of the W total, then you will have to go to chapter 13, okay, and solve it like 1 plus 2 multiplied by Z bar H, okay, you can and consider the AB factor and so on. So meaning that if the equipment is less than 25% of the total, also the same one, then you will go the seismic force of the non-building structure by chapter 13. Okay, however, regarding the supporting structures, if I have a supporting structures, then I will design it by chapter 12 or section 15.5. Okay, the other case, if I have the W non-building structures is more than the 25% of the W non plus W structure. Okay, so any analysis combining the structural characteristics of both the non-building structure and the supporting structures, meaning that I will do a structures combining the two buildings or the two components in the same one. However, if it is very rigid, if this W is very rigid, like it has a time period less than this 0.06 second, it is very difficult to achieve something like that. However, if it can be done, if it is rigid, for this part it is rigid, the supporting structures shall be designed by chapter 12, okay, and the R value of and you will use the R value of the main system. So if this equipment, if it consists let me draw it again. So if I have the same building here, but let me draw it like in 3D, and I have a structure, and this structure has an express in both direction, so it is very rigid, and the time period of it is lesser than 0.6 seconds, and its weight is more than the 25% of the total weight, okay, then I can design the building based on its R, okay, and consider this as a weight, as a dead weight. I will consider this equipment as a dead weight. Okay, and that is the design of the building. However, the design for the non-structural building, the non-building structures, it shall be chapter 13. So even though the W is more than 25%, but it is very rigid, you go to chapter 13. So to solve any chapter 13 or go to chapter 13 to solve any structural component, you must satisfy two conditions. The first one, if the equipment is less than 25% and it doesn't matter if it is flexible or rigid. The second one is the W is more than 25% but it is rigid. So I will go to chapter 13. Okay. The other case, okay, so I have the W equipment is more than 25%, but the time period is more 0.06 seconds, so it is flexible. Okay, so in this case, what I'm going to use, you will have to do an analysis for both of them, combining the two of them. Okay, and using the least R of any of them. So if you have a T non is more than 0.6 seconds, the non-building structures shall be modeled together. So modeling together in a combined model with appropriate stiffness. The R value, and that is the most important one, the lesser R value of the non-building structure or the supporting structures. So if I have it is an express, okay, so the R will equal to 3.25. Even so, I am using like here a special moment frame. R is equal to 8, so I will use the R equal to 3.5. So let's go back to the slides again. This one is related for the direction of loading. It is telling you that the combination that you are going to use, it is one of two criteria. The first one is 100% of one horizontal direction plus 30% for the perpendicular horizontal direction plus 30% of the forces for the vertical direction. This one it is specific for the hanging structures and the structures incorporating horizontal cantilevers. So if I have like a structures and I have like a horizontal cantilever, something like that, so and I have a long horizontal cantilever, it's like I have in pre-system. So the component for the hanging structures, something like that, however it's related to the non-building structures similar to or not similar to building, then I will use 100% from a horizontal direction plus 30% from the other horizontal direction, 100% here, 30% there, and 30% for the vertical distribution. The 30% of the vertical distribution, which is 0.2, I think is the SDS multiplied by the weight. So I will consider 30% of this value. Also the other one, 100% of the vertical direction and plus 30 of the horizontal, plus 30 another from the other direction. So for chapter 15 also we will talk briefly about it, like how to design it, what are the methods that you are going to use. So I highlighted you to use the most important parts. Also you should read it. Also this is a part of the weight, the selection intentionally left blank. Okay, this part is 15.3 telling you if it is less than 25 or greater than 25, and they give you if the fundamental period this one and so on. This is one I summarized it to you in the previous slides. Also that is there are two tables. One of these tables is for similar to building, the other one is not similar to building, so depending on which structures as a non-structural building that you are similar to building. So if you have like steel storage racks and so on, you can use this. If you have pipe racks, you can use this steel process structure and so on. If you have like not similar to building, like elevated tank, vessels, bins, hoovers, concrete chimney and stacks and so on, skirt supported vertical vessels, single pedestal or skirt supported, you will have to use this table. So get yourself familiar with these two types of table. That is one that we already talked about. So let's go now and talk about chapter 20. As I told you in the first of this session, we are going to calculate how to define how to determine what site class that we have. The start of this chapter, we will have to pass a lot of chapters like non-linear responses to analysis. I will not go through this. This one for the isolated structures. I think the 18 it is for damping systems, isolated damping system. With damping system, chapter 19. Just to get yourself familiar with the title of each of them. It said is the soil structure interaction for seismic design, because it's like the SSI and so on. Because if he mentioned something related to it, at least you know where you are going to locate to find it, and to find the location of it. So I will go to chapter 20 because it is a site class classification. According to ASCE, the site soil shall be classified in accordance with the table and a section based on the upper 30 meters. So if I have a location, my project location is here. So for the soil investigation report, I will need at least a borehole of depth equal to 30 meters at least to identify the site class. That is according to ASCE. However, of course, some boreholes, maybe like 15 meters or 20 meters, will be sufficient to determine the site class. So according to ASCE, the minimum depth to calculate it is 30 meters or 100 feet. The soil properties are not known in sufficient detail to determine the site class. Site class D, also subject to the requirement, shall be used. That is the same thing that has been mentioned in chapter 11. If you don't know the site class, then you will use D. Site classes A and B shall not be assigned to a site. That is a very important note. If there at least 3.1 meter of the soil between the rock surface and the bottom of the spread footing or mat foundation. So if I have a building and that is the foundation of the building, so I have, that is very rock, so that is rock, but at least the height is I have two cases. The first one, this H is less than 3.1 of like dense soil, okay, it's not rock, or the H is more than 3.1. In the case if it is the H is less than 3.1 meter, then I can consider site class A or B. If H is more than 3.1 meter, although I have a very large area of rock and so on, and that is the height of the bottom of the foundation. So I am measuring from here, not from the ground, okay, from the bottom of the foundation to the top of the rock soil. If it is more than that, then A and B will not be applied, so you can assume C. Okay, it is very important to note, because in some cases he will give you an example or a question where you can determine the site class. I will give you, let me draw again. So you have site class here. He will give you regions of site class, so you can able to calculate the VS as we will see now. So it's an important note to consider this one. That is, here we will only focus on the how to calculate the average shear wave velocity. So you have the summation of the di. The di is the thickness of any layer, as I told you. So I have this one, it is d1, this one is d2, and this one is d3. Okay, that is the summation of the layers, and he will determine the shear wave velocity for each one of them. So I have the shear wave velocity for this one, I have Vs1, Vs2, and Vs3. So to determine the average shear velocity, I will need to sum d1 plus d2 plus d3 and multiply d1 with the Vs1 divided plus d2 with corresponding Vs2 plus d3 corresponding to Vs3. And after getting the shear wave velocity like meter per second, I will go to the table to determine which site class is. If I saw hard rock and rock, so even though in the example that I have a very hard surface like rock surface, and that the distance between the bottom of the foundation and the top of this layer is more than 3.1, I cannot assume A or B, even though the the average shear velocity is satisfying the condition of this value 5,000 feet per second, or from 2005 to 5,000 to 5,000. This note, it is very important, because even though like in the exam he give you an example of this, you determine the site coefficient and the site classification and you are happy about it, but the distance between the bottom and the top is more than 3.1, so shall not be assigned. This note, it is existing here. Site classes A and B shall not be assigned to a site if there is more than 10 feet of the soil between the rock. Okay, so it's important to consider that. This is the table that we are going to use for the hard rock, and I also highlighted this to you because maybe in the equation he will tell you how to determine the site class, and after getting the site class you can calculate the SS and the S1 as the SDS and the SD1 and so on, and you can determine the seismic design category. So maybe in an example he will tell you I have a building, okay, and I have the layers, and I need to determine the seismic design category of the building. So of course I need to get the site class. Okay, he gave me the SS and the S1, they are given. Okay, so after that I will calculate the SDS, which is equal to 2/3 of the SMS, which is equal to SS multiplied by FA, and the SD1, which is equal to 1/3 SD1 SDS multiplied by FV, I think. SS and no, that is the S1, and after getting the SD1 and the SDS, okay, and knowing the risk category and the FA and FV depending on the site class, okay. So after knowing all of this, I can determine which seismic design category the building is. That is the type of the questions that you are going to see in the exam. Okay, he will not give you like a very forward. They are very forward, but you need to understand the relationship between each one. Now we will talk about the IBC 2018 and ASCE. According to the IBC, you will use. He is like the wind. He is agreeing to consider the ASCE methods. However, there are maps for the SS and the S1. And as I told you before in the start of this session, I don't think he will let you use these maps because it is very difficult to use it. Okay, and I think in according to America, USA, they have a website. You can enter the longitude and the latitude, and you will get the SS and the S1 for the structure. Okay. Okay, so in the exam he will give it to you. If you need to calculate anything based on these values, he will give it to you because it is very difficult to get the SS and the S1. So for the part of the nutshell, we shall focus on some important points, starting of course from chapter 11. You need to focus on chapter 11 because it is a design criteria of the seismic force. It gives you the main points that you need to focus on and the main factors like the FA and FV, the SDS. He talks about the response spectrum. If the site class is not given, then you can use D. It tells you also the seismic design category. It gives you a lot of cases and conditions that you need to focus on. Also, it has a few pages, okay, so you will not spend a lot of time in this one. The other points, of course, is the diaphragm, and as I told you in the first session, in this part, that at least 3 questions having the same idea from the book that I gave you below in the description of this one regarding the diaphragms. As you can see, that is the diaphragm, and I highlighted you the most important one, but as I will tell you again, I highly recommend to solve chapter 1 and chapter 3 completely because it has a lot of ideas and good ideas. Okay, so be prepared in the exam, and these questions will be an easy for you when you will see it in the exam. Also, another important part, if you have like an SS is lesser than 0.15 and S1 is lesser than 0.04, then you will have to consider the seismic design category A. And the minimum force acting on it, it will be from chapter 1, as we told before, it will be at least 1% of the own weight of the structure, of the dead weight. So if he give you an example in the exam that this structure is seismic design category A, then at least the minimum base shear will acting on it, it will be 1% of its own dead weight. Also, another important thing, if the site class is not given, use site class D, because sometimes he will give you like a lot of data and he wants you to calculate it. Like this one, I cannot calculate the FA and the FV because I need to know the site class. So he gave me the SS and the S1, and he doesn't give me the site class. In the case he doesn't give you the site class and he doesn't give you any information related to it, okay, it is like a stiff soil or any type of soil like here in chapter 20, this is the site class. So he didn't give me any site class. It is rock, it is a very dense soil and soft rock. It doesn't give me any shear velocity. So if he doesn't give me the shear wave velocity and he doesn't give me any site class, then in that case I will consider site class D. Okay, and I will get my SMS and SM1 and I will get my SDS and SD1. So it is another important, because in the exam he will not tell you. Okay, so you must understand, if I don't have enough information in the site class, we use site class D, and actually we use this in our actual work. If I don't have any geotechnical report at the start of the project, I will consider as site class D, and I will build my assumption until I have like a detailed geotechnical report, and it will tell me what type of site class, whether it is C or D or E maybe. Also, another important point, if T is not given, if the time period is not given, so I have a structure as I told you before, that is if I have like a structure, okay, and he just gave me the number of stories equal like 10 story, and the h average of the story height, okay, that is the average story height, is approximate like 12 feet. Okay, it doesn't give me the total h, I don't know the total h. Okay, and of course he will tell me like I need to calculate the time period maybe. So the time period approximate, it will be 0.1 multiplied by the number of stories. Okay, so he will not tell you how to calculate the time period and so on. So you need to know these values beforehand, that there are approximate value for the t for the fundamental, and you can get it from these equations. Okay, and also if he give me like the type of the structures, if he give me the total height of the structure, I can calculate the time period. Another important point to check the limits. So if in the same example he gave me the time period of the structure, so the time period of the structure is like 1.2 seconds. Okay, I need to check the upper limit. So still I will need to calculate the t approximate. So maybe he gave me the height and so on, so I will calculate the t approximate based on the type of the statical system, whether it is a moment or other or whatever. Okay, and after checking it, I will check my limit cu multiplied by t approximate, and to make sure my time period is lesser than this value. Okay, so it is also important to check the limits when he give you an equation. When he give you like the question in the exam, you need to check the limits. So in the case if he give me the time period for the structure, the fundamental period, and I shall calculate the force, like in this part 12.8 I think, yes, that is the one. So I need to check the limits. So he give me the time period and so on, but I need to check the time period of the structure to be lesser than the cu in this part. My structure shall be less than the cu multiplied by the t. Okay, so if my time period, the given time period, is more than the cu multiplied by the t approximate, then I will use in this equation the cu multiplied by the t approximate. Okay, so that is the idea to consider the limits when you are calculating the equation. Also another important point regarding the site class, sometimes the simplified method seismic base shear, it is very important, because he will tell you that you have a rock site, okay, and he will just give you the SS, and he will tell you that I need to calculate it. I have like 1 story or 2 story or 3 story. So it is also an important method to consider it, because sometimes he will tell you, he will not give you enough information, and you should consider also this method. Okay, you should consider also this method when you are calculating the base shear on a building. So just focus on the diaphragm. At least 3 questions will be in the exam. It is very important part, and as I told you, in these parts you need to focus on. Of course there is chapter 13 and also chapter 15. Just to you have the general idea of them. Okay, that these ones are for the structural. Chapter 13 is for non-structural component. Okay, it is for the non-structural component, so you just need to focus on how to calculate the base shear of this equation and the relation of the z plus h, and understand what is the AB factor, what is the IB factor, so you have the general idea, because if you had this question in the exam, you already know what are these factors. Okay, also for chapter 15, chapter 14 is dedicated for the material, and chapter 15 it is dedicated for the non-building structures. So if your system is lesser, if it tells you that I have equipment and it is non-structural building and its own weight is lesser than 25%, okay, then you will have to go and to solve it. If it is less than 25%, then you will have to go at chapter 13. And if it is more than 25% and it is very rigid, you will have to go also chapter 13. And if it is the own weight is more than 25%, however the time period is more than this value, so it is a flexible, then you will model them together and you will use the lesser r and so on. So you get the general idea of it, okay? Because these are the special topics, and I don't think he will go deep into them, but still you must know the general idea of chapter 13 and chapter 15. And also I told you about chapter 20, where you can calculate the base shear or seismic force at site classification, and don't forget about the site classes. If it is more than 3.1 a soil, then after that a rock, the A and B will not be assigned to a site. You will, I think in the book there is an example having this one, I think is that is the one. Okay, so he will tell you how to calculate the base shear under each building. Okay, so it is also an important, so you will have to consider how to calculate the base shear under the building by using the average wave shear velocity. So that's all for the in a nutshell. Just focus on the diaphragm and to have a general information about each point, and don't forget to use the limits. Now for the example part, the first example, it is very straightforward, where we will be able to apply all the how to calculate the seismic force on a structural building, and what are the steps that we are going to use. So this one it will be a comprehensive way to how to calculate everything, as you can see. A good practice when you are reading any questions, especially for the seismic, of course, and the wind and so on, for each sentence you must extract data. So let's start with we have a residential. So I have a residential 3-story residential, meaning that I have a risk category 2. Okay, the importance factor is equal to 1. Okay, this one go to chapter 1 and get this value. However, we know the risk category also, we already know that the residential is 2. We have a moment resisting frame, so I have a moment resisting frame, okay, on a rock soil. Okay, I have a rock soil. So what is my site class? Site class will be, let's go to chapter 20 and to check it. Site class, I have a rock soil, site class rock, so it will be site class B, and the wave and the shear wave velocity, it will be from 2500 to 5000. Okay, so my site class will be B, and the shear wave velocity from 2500 to 5105 feet per second. Also, he tells me that I have the spectral response acceleration have been mapped for values on the risk targeted maximum considered earthquake. Okay, we already know the difference between the MCE and the MCG. One is used for the building, which is the MCE, so it's good, it's correct one, and the other it is used for the liquefaction and for soil stability study and so on, the big ground acceleration and so on. That is the SS. He gave me the SS, and he gave me also the S1. The first question, he tells me that to compute the site classification and the shear wave velocity, we already calculated. The rock soil is this B from chapter 20. So if you don't know which chapter that you are going to use, it will be a difficult question for you. You don't know what is site classification, and if you just go on the exam and just searching for the site classification, starting from chapter 11, it will give you the site classification. So you will it will take you a lot of time to able to go to chapter 20. So it is a good practice to know what each chapter is talking about. So compute the site classification, it is B, and the shear wave velocity ranging from these values. The second one, it tells you that to compute the 5% damped spectral acceleration for the SDS and SD1. So after getting the site classification, I will have to go to chapter 11, because it is a seismic design criteria, okay, where I will be able to calculate my FA and FV based on the SS he is given to me. It is more than 1.5 or from equal to more than, and site class B, so it will be 0.9, that is the FA, and the FV for the S1 it is given to me, it is 0.6, and it is my site class is B, so it will be 0.8. Okay, and after getting them I will get my SMS and the SM1, and after that I will get my SDS and get my SD1. So this one also is easy. Number 3 tells me what is the risk category. We already told it is risk category 2. Number 4 the importance factor, we also talked about it is a risk category 1, importance factor 1. The number 5 tells me it is to determine the fundamental period of vibration. So we have two approximate methods. The first method that we know about, the T approximate is equal to CT multiplied by H multiplied by power to X, and the T approximate is equal to 0.1 multiplied by N in case of depending on two cases, that you are using moment frame. So I am using moment frame, and the average story is more than 10 feet. So I am using actually moment resisting frame, and my average is 16, as you can see. So this one will give me like 0.1 multiplied by 3 story. I have a 1, 2, 3, so it will give me like 0.3. And the other one, it will depend on the factors that I'm going to get from chapter 12. Okay, it will be something like 1.2. Yes, that is the one. 12.8, it is very important to determine the period determination and to calculate the shear. 12.8, you must memorize this clause 12.8, because it is the one that calculate the equivalent lateral force, what is the time approximate period, and so on. It is very important in chapter 12. So I have a steel moment resisting frame, and these values in the equation or in the example he gave me in feet. So I will use the 0.028, and corresponding to it the x value, which is 0.8. So I will calculate this one based on the shown value as we saw, and to determine the fundamental period. Okay, in the exam he will just give you like he will not give you the two answers. I think he will not give you the two answers, only just one of them. But if this answer is not mentioned in the choices, then you will have to use this one. The other thing, to determine the response modification factor, which is R. So in chapter 12 I will have to go why to chapter 12? Because it is a residential building. So if he told me that this building is inhabiting equipment, I will have to go chapter 15. So it is very important. Okay, so I am a residential, then I will go to chapter 12 and get it from the table. So let's go at the start of chapter 12. That is the one. So he tells me that I have a steel moment frame. He doesn't tell me it is ordinary or intermediate. Maybe I will consider it as an ordinary. Then it will be 3.2, 3.5. He tells that is the R factor. Okay, the first one, it is a response modification factor, R. Okay, that is the response modification coefficient, or the R value. So it is very important to know even the naming of each coefficient and so on. He tells you that compute the seismic response coefficient. Okay, let me clear all of this. So he tells you that to calculate. So we already finished all of this. Number 7 can compute the seismic response coefficient. The seismic response coefficient is the CS value. So I have my base shear multiplied by CS multiplied by W, the effective weight. So the CS he tells me to calculate it. So we know from also from clause 12, 12.8, which is 102. That is the CS value. Okay, so the CS value shall be based on the SDS or the this value. So I have my R, my I, and you have to check also the limits, as I told you before. My T is the TL. We usually take it as 8 seconds, and of course it will the EURT like 95% or 90% of chances it will be lesser than the T long time period, the TL. Of course, you shall not forget to calculate the minimum. That is the important part here. Okay, and he tells you something also important. In addition, for structures located where S1 is equal to or greater than 0.6 shall not be less than this one. In our case, so it is like a regular case, the S1 is equal 0.6. So this one you will have to satisfy. Okay, this one you will have also to satisfy. So you will have to satisfy this one and also this one. So it is very important question how to calculate the response modification factor. As I told you before, don't forget the limits. The oldest trick in the exam regarding the limits. Okay, he will trick you in the limits. So I calculate the S directly. Don't check the limits. Not checking the limits. Okay, it will be wrong. You must check the limits. Compute the seismic load at the structure's base footing. Okay, we know that it will act at here. So V multiplied by CS multiplies the W, and the W he gave me the seismic weight. So it will be the submission. Kips in the first session, or in the second session, I told you the Kips is almost equal to 4.45 kilonewton. It is kilopound. Okay, if you need to transfer it into metric. Again, he will tell you, so it is an easy one, the 8th. Compute the lateral load on each floor. Of course, that is one is very important, because after getting the T approximate, you will have to check it if it is like more than 0.5 second or not. Because if it is more than 0.5 second, okay, in this case, the distribution will not be uniform. Okay, it will be like parabolic maybe, so it will have a parabolic shape of the distribution of the vertical forces. So we will have to go to the vertical distribution. Let me check where's the vertical distribution. I think it is up. That is the diaphragm. Scaling. Yes, that is the one. The vertical distribution, it is also important because if the time period, if for structures that have a period 0.5 or less, then I will use k equal to 1. However, if it is more than 0.5 and lesser than 2.5, then the k value it will be ranging from 1 to 2. So after checking or after calculating the time period of the structure, you will have to check the k factors that you are going to use. Then after that, you will consider this equation to calculate the base shear on each floor. Okay. So the first question, it is very informative and it is highly recommended to solve it because it will give you the confidence on how to use this chapter, because it is starting from chapter 11 to chapter 1 to determine the risk category and the importance factor, to chapter 20 to determine the site class, to chapter 12 to solve the problem. So it has a combination of chapters to solve this example. It is highly recommended to solve it by your hand. Another example, this one, it is a theoretical one. He tells you which of the following statement is truly related to seismic parameters. Building acceleration is larger on soft soil than on dense soil medium. The second one, in a rigid structure, the maximum acceleration is equal to in a rigid structure, the maximum acceleration is equal to ground acceleration. Increasing the stiffness of a building increases the natural period of vibration. And the fourth one, a flexible building has a larger period of vibration and a lower maximum acceleration than a rigid structure. This picture I provided, okay, it is not in the exam, but I provided with the example. So to understand the response spectrum for each type of site class. So I have like the same seismic force and I have the same time period for the building, but my site class or my type of the soil is very different. So if I have the same parameters regarding the building and so on, however the site class is hard soil, the response spectrum will act like this. Okay, it will be shifted and going back to the acceleration part because the response modification is actually it can be divided into 3 parts. Here we can tell it is a displacement. This one it is for velocity, and the third one will be acceleration. So I have, if my site class is hard soil, it will go to the acceleration part. Let me. So the first answer, the first choice, one only, building acceleration is larger on soft soil than on dense soil. No. From here, no, of course not. The A is wrong. 1 and 2, okay, 1 is wrong, then I will not consider B because 1 is wrong. So of course 2 will be wrong, or 2 will not be wrong, but the answer B is wrong. So A is wrong. So B, because it has 1, it will be also wrong. So the third answer is 2 and 3. Okay, increasing the stiffness of a building, increasing the natural period of vibration. Okay, we already know the equation of the time period, the relation between the time period and the stiffness. For a single degree of freedom, it will be something like that. So if I increase my K, increasing the stiffness, increasing the natural, no, increasing K, the time period will decrease. So 3 is wrong. So C is wrong. So the only answer is giving for me is B, D. So it will be D. So D, in a rigid structure, the maximum acceleration is equal to the ground acceleration. Yes, this point, as I talked to you before, if that is the point where the ground acceleration, it is the ground acceleration. So if it is very rigid, it will the structure acceleration will be the same as for the ground acceleration. Okay, for a flexible building has a larger period of a vibration and a lower maximum acceleration than a rigid structure. Okay, so if I have a flexible building, so my time period, it will be something like here. So has a larger period of vibration, yes, and a lower maximum acceleration than a rigid structure, yes, and a lower maximum acceleration, yes, it will be something like here. So it has a lower acceleration than a rigid structure, because my rigid structure will be located something like here, so it will has like the SDS. So it will be 2 and 4. So again, you should consider theoretical questions in the exam, and to understand, so you must have the understanding of like the response modification and so on, so you will be able to solve it. Let's go for example 3, and it is a diaphragm, of course. He is giving to you that is the lateral force. Okay, he tells me that I have a chord force, that is the shear walls chords, that is the top chord, bottom chord, and that is the top chord, the shear on diaphragm and the moment on diaphragm. Of course, this example, it will not be giving to you like this one, it will be give you like this one. Okay, and and after that I will open the book, and let's go and check the most common examples that you are going to use. He tells me here, for the plan view of the building shown below, what is the resulting chord force. So the first thing, what is the chord force? The chord force, that is the one, as I told you, you can consider this as a deep beam. So I have like a frame, and I have a uniform force, so the moment will be something like that. So that is my top chord, and that is my bottom chord. So he tells you to determine the chord force from the lateral loading. So I will can from this uniform load, and regarding this statical system that I'm using, so the moment here will be like WL squared divided by 8. So what is the L? It is 35, and what is the W? The lateral force. So after getting the moment, I divide it by the depth. Okay, it is the same as if I have a truss. So if I have a truss, to determine the bottom chord and the top chord, after getting the moment, you will divide it by its own depth. So it is the same idea. You will divide it by the depth, then you will have to calculate the chord force. So this one is easy, but you will have to consider, of course, solving from this example. It is very important, because in the exam he will not tell you if I have a flexible diaphragm or a not flexible diaphragm. So let's stop here. Okay, the main idea of the diaphragm, the main two questions. The first case A, if my diaphragm is flexible. In the exam, he will not tell you that it is a flexible, but he will tell you that I have like a wooden panel. So if you have like a wooden panel, then you will have to consider it as a flexible. So he will not tell you it is very flexible or it is not flexible, but he will tell you that this roof is wooden panel. Maybe it is like a cast in situ concrete. So if it is cast in situ concrete, so I will consider it as a rigid. So in the case of a wooden panel, so it will be a flexible. So if I have like uniform force, okay, and I have a shear wall here and shear walls there, okay, and another shear wall, okay, he will tell you the first equation to calculate the forces on the maybe shear wall 2. Okay, he give me this L1 and this one is L2. Okay, if it is flexible, then as I told you before, it is based on the area tributary. So the force will be equal to W. So I will have like a W multiplied by L1 plus L2 divided by 2. That is the force acting on shear wall 2. Okay, that is the first thing. Another important, if you want this, you to calculate the chord force here or there. Okay, so the moment will be something like this. It will be act as a simple beam. Okay, it will act as a simple beam. So it is a simple beam because it is flexible. So it will act as a simple. So if he wants you to calculate the forces here, then it will be as we know this W multiplied by L1 squared divided by 8, and if I have my width B multiplied by B, so I will have my chord force. Okay, that is the idea of being flexible. The other case, if he tells me that it is rigid, so if I have my rigid structure like this one, so I have a rigid. Another thing also regarding the flexible, because it is the old trick in the exam, he will give you the same one, okay, and he will give you for the each shear wall a rigidity. But in the equation he will tell you I have a wooden panel. Wooden meaning flexible. Okay, so still I have my L1 and L2. So the shear force for shear wall 2, it will be still on the tributary area. But he gave me the rigidity, okay, but it is a wooden panel. It doesn't differ if he give you rigidity, if he give you, it is very extreme rigid, okay, but the forces will transfer from what transfer from the wooden panel, from the diaphragm to the lateral resisting system, okay. So still it is flexible, so it is still based on the tributary area. Now for the case of rigidity, if I in case 2 I have a rigid structure, and as I told you, he will not tell you I have a rigid cast in situ, maybe concrete and so on, rigid slab, and he will give you like shear walls here. So I have an R equal to 3, this one equal to 5, that one equal to maybe 2. It tells you I need to calculate the base shear at this one, and he give me the lateral force. It will be based on the base shear for shear 2. It will be based on the rigidity. So I have my W multiplied by L1 plus L2. Okay, that is L2 and that is the L1. Okay, multiplied by R5, that is the rigidity, divided by 5 plus 3 plus 2. It will be based on the rigidity. So I can consider the base shear and calculate the base shear according to the rigidity. So that is the main idea that you will see in the exam regarding the flexible diaphragm and the rigid diaphragm. You must understand the difference between them because, as I told you, he will try and to trick you, and also to focus on this type of exams, because as you can see there are a lot of questions regarding it, and no worries, the answer is very informative. Okay, the solution is very informative. Now for example 4, it will be the same as example 3. However, this one it will consider the center of mass and the center of rigidity, and of course, as I told you, to include the accidental eccentricity, which is 5%. In the exam, he will tell you that you have like an equivalent lateral force or the base shear, and to calculate the forces, the maximum forces on this wall, maybe, or in that wall, he will give you that is the wall 1, wall 2, wall 3, wall 4, and so on. and he will give you the center of mass and the center of rigidity. You can calculate it. Okay, the center of mass, maybe he will give it to you, or he will tell you that it is in the middle of the building. So after getting the center of rigidity and after getting knowing the center of mass, if he is not giving to you, then you will have to consider in the middle of the structure, and of course to calculate the torsional generated from the inherent torsion. Okay, and of course to consider the accidental eccentricity which will increase the shear force on the corresponding walls that you need to carry. So if I have like this one, this is my wall 1, it will give you like this. You have a wall 1, you have a wall 2, maybe you will have a like wall 3, and that is maybe another wall. So you will calculate the x for rigidity and to calculate the y rigidity, okay, for depending on the each wall, and after getting them it will be something like here, that is the center of rigidity. I have like L1 and L2, so I will consider the center. If he doesn't mention, he doesn't give me the center of mass, then I will consider in the middle, that's the center of mass. Okay, he tells me that to calculate the base shear or the shear force on this wall, maybe wall 1. So if this force will be transmitted, we know it will act on the center of mass and it will transfer to the center of rigidity, so it will be something like that. So the walls will act in a way opposing the moment. So if the moment is moving like counterclockwise, then they will move like clockwise. That is the resistance of the wall. Okay, so that is the resisting force. Okay, so and the base shear where it will get it is coming from this way. So also the walls in this direction parallel to the direction, it will also act this way. So I consider the inherent torsion and consider the actual force coming from here, which acting on this wall. The third one will be the accidental eccentricity. So if I consider like 5% from L1, so if I consider the 5% from the L1, I will take it right, or I should take it left. If I take it to the right, it will increase the eccentricity between each of them, which will result in a more force on that one. So in this example, I will consider it as a right, so I will consider an additional eccentricity or the additional moment generated from the 5%. Okay, so I will not consider from left because it will give me a lesser force, so I will consider the one that will lead to a maximum eccentricity. Okay, for example 5, determine the seismic base shear for a 3-story building. So I have a 3-story shown below as a building frame structure with bearing wall, intermediate reinforced masonry, shear walls. This definition we will get it from the table from chapter 12 to get the R factor using the simplified procedures outlined. Okay, what is the simplified procedure outlined? So if you don't know these simplified procedures, you will waste your time checking it in the chapter 12. Okay, so I will go to slide 45 and I will consider. He didn't tell me what type of rock site, what type of site. Then I will consider the worst, 1.4. If he doesn't give it to you, then I will consider the worst, which is 1.4. He gave me the S, I think. He gave you the SS, so I can calculate my SDS. The R factor I will get it from the table. I have a 3-story, then I will have an F factor of 1.2. So I can calculate the base shear and the W, the effective weight. He has given to me like the effective seismic weight of each floor is 235 kips. I have 3, then I will multiply this weight by 3. So it is a very straightforward questions, but if you don't know where to look up for the equations, it will take time from you. Also consider these questions if it was like number 60, okay, because the exam it has 80 questions. So if this one is like number 80, you don't know the idea, you will not have enough energy to look it up and so on. So as I told you, it is a good idea to to have a lot of information and to have to be familiar with the code. So it will be easy for you to go and back from the exam and for each code and so on. To recap it again, don't forget to solve this one. I will leave it, solve this book, I will leave it in the description. To focus on chapter 11, 12, to have a knowledge of chapter 13 and 15 and 20, and to consider the minimum limits and so on. And it will be an easy exam, of course, and the questions will be guaranteed, and you will solve it correctly, inshallah. Thank you for watching, and see you in another video.